Electricity powers our modern world, from the light in your classroom to the trains rushing through a city. But have you ever wondered how such a complex system is monitored, controlled, and kept reliable? In this video, we'll explore the fascinating world of power system operation and control with a special focus on operating states, control objectives, preventive and emergency measures, energy management systems, and SCADA. A power system doesn't always run smoothly. Its behavior changes depending on disturbances, demand, or faults. Engineers classify the operating states into 5 categories. In the normal state, everything is balanced. Generation matches demand, reserves are adequate, and the system is secure. In the alert state, the system still works, but reserves are low. Any disturbance could push it into trouble. Next is the emergency state, often caused by sudden imbalance between generation and demand. Here, operators may need drastic actions like load shedding or generation cutbacks. If things worsen, the system falls into the in extremis state. Both generation and demand constraints are violated, and parts of the grid may collapse. Finally, comes the restorative state, where the system is slowly brought back to either alert or normal conditions. These states highlight why constant monitoring and quick action are critical in power system operations. So, what do operators aim to achieve while controlling a power system? There are 3 main objectives. Match generation with demand. Since electricity cannot be stored easily, supply must follow load instantly. Maintain power quality, ensuring voltage, frequency, and wave shape stay within limits. Operate economically, providing electricity at the lowest possible cost without compromising reliability. This is achieved through layers of control, from prime mover and excitation controls in generators to transmission devices like tap-changing transformers and down to distribution systems ensuring proper voltage at the consumer end. Reliability in power systems comes down to 7 key ideas. Always balance generation with load using tools like automatic generation control. Keep reactive power in check to maintain voltage stability. Ensure thermal limits of transmission lines aren't exceeded. Maintain stability, both angle and voltage stability, so generators remain in synchronism. Satisfy the N1 reliability criterion, meaning the grid should survive even if the largest generator fails. Plan and design for safe operations and always be prepared for emergencies. Together, these principles ensure that the lights don't go out. To keep the grid safe, engineers use 2 types of controls. Preventive controls are proactive. These include rescheduling generation, starting up reserve units, switching shunt capacitors, adjusting fax devices, or even changing substation configurations, all to keep the system in normal or alert states. Emergency controls are reactive. When things go wrong, operators may shed load, trip generators, block transformer taps, or even split the grid into smaller islands to prevent total collapse. Think of it as the difference between taking vitamins to prevent illness versus calling an ambulance when a health crisis strikes. At the heart of modern grids is the Energy Management System, or EMS. It's like the brain of the power system, continuously monitoring, analyzing, and optimizing operations. EMS has 3 levels of objectives. Primary, maintain frequency, voltages, and tie line power within limits. Secondary, achieve economic operation through optimal dispatch. Tertiary, handle planning, maintenance scheduling, and long-term optimization. An EMS consists of SCADA for monitoring, computers for fast calculations, user-friendly graphical interfaces, and application software. SCADA, short for supervisory control and data acquisition, is the backbone of power automation. It collects data from sensors across substations and transmission lines, sends it to a central control room, and enables operators to take decisions. A SCADA system has 5 components: remote terminal units and IEDs to gather data, communication systems, master station and user interface, field instruments, and software for real-time control. SCADA ensures that every fault, alarm, or change in power flow is instantly visible to engineers. In summary, power system operation and control is about more than just generating electricity. It's about keeping the grid stable, reliable, and efficient under all conditions. From understanding operating states and control objectives, to preventive and emergency measures, and finally to advanced systems like EMS and SCADA. These concepts form the backbone of modern electrical engineering. As future engineers, you will play a key role in ensuring that the power systems of tomorrow, integrated with renewable energy and smart grids, remain robust and reliable.